everyone. Okay, so this is going to be a little bit of a longer video where I really walk through how to use Gauss's law. And in particular, we're going to talk about how to use Gauss's law for an infinitely charged surface or an infinitely charged plane. So maybe the first thing that we want to think about is like, what's the goal? What does using Gauss's law actually give us? The beauty of Gauss's law is that if we know something about our enclosed charge, we can figure out what our electric field is. So the whole goal is, what is E? That's the goal. That's what we're aiming for. What is my electric field? All right, so the first thing I want to do is I'm going to draw a picture. So I'm going to set up my coordinate system first. So I'm going to call that my Z direction. This will be my X direction. That's my Y direction. That's what we're going to be working with today. Now I'm going to put my infinite plane on the surface of the XY plane. So imagine that the entire XY plane is positively charged and it's uniformly distributed. Okay, so this is my XY plane. I'm going to just draw the negative Y hat direction and the negative Z direction there. So pretend the whole surface is positively charged with some uniform distribution. So I'm going to put that we've got some sigma here, right? Some sigma. Okay. Let me see if I can get a better pen here. Sigma. Oh, good. So that whole XY plane is positively charged and it's uniformly distributed. The charge is uniformly distributed on that plane. Okay. So we've got that settled. The first thing let's think about is we have some uniformly distributed charge. What does that actually even look like? Well, what we can do is we know that our sigma is constant. It's uniform across the whole surface. So very simply, we can just start to draw these little plus charges. Here's my charge diagram for this infinitely charged surface. And it's going to go like this forever, right? It's going to go like this forever. It'll be uniformly distributed everywhere across the XY plane. There's no cluster of more positive charge in this area. There's no more negative charge. It's all positively charged. So that's sort of what our general charge diagram might look like. Okay, so let's think about the electric field from this infinitely charged. Let's just think about the direction for a second. So this is an infinitely charged surface, as I've said. We've got positive charges here. We know that positive charges produce an electric field that point radially outwards. So what this means is that a positive charge over here, and if I want to keep drawing some positive charges over here, a positive charge over here is going to produce an electric field. Some of it will be pointing directly upwards and directly downwards. Some of that will be pointing in this sort of Y direction, maybe some in the X direction, and some going that way. But we have a similar one over here. So for every charge we have on this side, we have a matching charge on this side because it's infinite. What that means is that your electric field components in the X and Y direction are going to cancel out, and you will only get a net electric field in the Z direction. We're back. So for Z greater than 0, so when we are above this XY plane, we should expect that these positive charges, like we just said, their X and Y components are going to cancel, and we will only get a net Z direction. So we should expect that our E is going to be pointing upwards in the Z hat direction. So E, let's say we'll set it equal to like E Z hat. And for below the surface, in a similar argument, we'll have positive charge that's producing a net electric field in the minus Z hat direction. So I can write that below Z is equal to 0, we'll get that this is minus Z hat, right? Okay, so we know that we don't have any X component, we don't have any Y component, we only have a Z component since this plane is infinite. So the next step that we want to do is we need to choose a Gaussian surface. So that's the whole purpose of this side of the integral, is we want to figure out the net flux through a surface that surrounds some of our charge. For an infinite plane, I'm going to choose a box that looks something like this. And this box will extend above and below the surface, right? So let's see if I want to draw this like this. Right, above and below the surface I have this box, and we'll say that it has lengths L. So there's my Gaussian surface. That's what I'm going to use to figure out what my E field actually is, what the form of my E field is. Okay, so now what we need to do is, here's our surface. We need to figure out the net flux through the entire thing. And what this means is we need to figure out the flux through each surface individually and add them up. So we need to think about the flux through the top, the flux through the bottom, and the flux through the edges. Let's start with the edges. Let's start with the edges. So we'll call this side L as well. It's a cube of length L, even though it looks like a rectangle. All right. So for each of the edges, they have their own A vector, right? We need to also define what our A vector is. Let's think about one edge first, and then we'll see if we can sort of reason our way to the other edges. And I'll start with this edge over here. And this edge has some area vector A that's pointing in the positive y hat direction, and it looks like it has an area of, let's see, L squared times L times L. So L squared y hat is my area for that surface at the edge there. Okay, that's fine. But let's think about the flux through that surface. And the flux through that surface is given by this dot product, right? I think immediately we can look at this and we can say, well, E dot dA for the edges is going to be z hat dotted with, in this case, a y hat, right? But that's equal to 0. The dot product between these two unit vectors is going to be equal to 0, right? This dot product only nicely picks up the sort of matching components, right? If we think back to our calculus classes. Okay, so we've got that edge, but can we extend a similar argument to the other edges? And I think we can. We have this area that is pointing in the y hat direction. This area is pointing in the z hat. This area on this edge over here is pointing in the minus y hat, and the edge in the back is pointing in the minus z hat direction. Well, we're going to get a similar thing here with each of those edges, where z hat dotted with x hat is still going to be equal to 0. So all of our edges are producing a flux. The net flux through those edges is going to be equal to 0, right? You can write this as phi sub e. Okay, so that's nice. That's like one less thing that we need to worry about. Now let's think about the top and the bottom. So let's see, let's write the top. The top and the bottom. So now we know we've got this z hat components here. And for the top, let's start with the top. This is my z hat there, right? Well, that's really nice. So let's think about what this, let's E dot dA here. So usually we think about maybe dA as, let's see, as like, in this case it'd be like dx dy, right? We have some little piece of area on this plane here. That little area is going to be dx times dy. So when we have this integral, we have this electric field dotted with dA, where dA is going to be our dx dy. And this is all nice, this dot product works out because we said that above z equals 0, our electric field points in the positive z hat direction, and this A has a vector pointing in the positive z hat direction. The A vector always has a vector perpendicular to the surface. But remember that we already said that our electric field does not depend on x and y, right? No matter where I am on the infinite plane, in this plane, right, in the xy plane, the electric field is going to be the same. It's going to be pointing in the z hat direction. So what that means is that when we think about this integral here, this E does not depend on dx and dy. So do we need to actually do the full integral? No, we don't. E is not dependent on x and y. We can pull this out of the integral, and then we see that this is just the integral over the surface, and that gives us just the area of the surface that we're looking at. So Gauss's law for the top actually reduces to, and I guess if we're just looking through a surface, this isn't Gauss's law, we're not looking through the full surface yet, just through the top. If we want to think about the flux through that surface, E dot dA. Now notice I don't have a circle here. That's because I'm not looking at a closed surface. I'm not looking at the whole surface. I'm just looking at this surface here. E dot dA. This is going to look like, we've got our EZ hat dotted with dx dy. Now this is a z hat. Those go away nicely. We said that E doesn't depend on x and y, which means we can pull it out of the integral. And then we're left with just the integral over dx dy. Right? So let me be really clear about this. So we write that this is then equal to E times dx dy. Well, this is just the area times the area. Right? And now I've said that my area here, I've defined my Gaussian surface so that my area is equal to L squared. So we've figured out that our flux through the top is equal to E times L squared. Okay. Now is it true for the bottom as well? Yes, I think so. The only difference between the top and the bottom is that instead of having EZ hat, we have E minus Z hat. And then for the area vector, this one is pointing in the negative Z hat direction, right? So we end up getting, if we look at this, and we want to do a similar thing for the bottom, we have E minus Z hat going the minus direction, dotted with a minus Z hat. The minus signs cancel, and you get the same thing. So, let's see. So I can write the top and the bottom is going to be really, really similar, right? Where we get that our flux through that surface is going to be equal to the same thing here, EL squared. Now Gauss's law is telling me about my net flux through the surface. Right? I need to add up all the flux going out of all of the different surfaces to be able to do the Q enclosed over epsilon naught. So the left-hand side of this equation is going to be adding up all of our fluxes. We have 0 for all of the edges, so we'll have 0 plus 0 plus 0 plus 0, right? Plus 2 EL squared. So this is equal to 2 EL squared. Okay, that's nice. But now I think we need to think about, right, what is this Q enclosed? What is my Q enclosed? So let's think about this sigma. Sigma, we said, was uniform across the whole plane. And so we can use our sigma to understand what our total Q enclosed is in the surface, right? So in the surface, along this plane here, remember that our sigma has units of like, it's like dq over dA, and I'm going to write that as dx dy. This is uniform, so I can sort of look macroscopically, and I can say that sigma is equal to the Q enclosed by my surface, right? The Q enclosed by my surface divided by the area that's inside my surface here. And that area is going to be L squared times L squared. So we get L squared in the denominator there is my sigma. We can rewrite this for Q enclosed to be equal to L squared times sigma. And now let's put the pieces together. We have here, and we have here. And then we have this. So I'm going to write this as, I'll write out Gauss's law again. E dot dA is equal to Q enclosed over epsilon naught. We figured out that our net flux through the surface is 2E L squared. And that's equal to Q enclosed over epsilon naught. So we got L squared sigma over epsilon naught. Now let's simplify and solve for E. So E is going to be equal to L squared cancel, sigma over 2 epsilon naught. And let's be really specific because we want to make sure that we are labeling our electric field as vectors. So what I'm going to do here is I'm going to say for z greater than 0, right? I'm just going to use this exactly there. For z greater than 0, our electric field should be sigma over 2 epsilon naught z hat. And for z less than 0, E is going to be minus sigma over 2 epsilon naught times z hat. Right? Okay. So that is how we use Gauss's law, right? Let me walk through the overall sort of steps that we took here because it's a little bit all over the place. So let's walk through it just really quickly. Our goal of using Gauss's law was to figure out what our electric field is, given some charge distribution. In this case, I had an infinitely charged plane here that I wanted to figure out what my electric field is. I started by thinking about what the direction of the electric field is above and below the surface. And we found out that there's no x and y components because we have an infinitely charged plane here, where the x and y components will cancel, and you'll just get a net electric field in the z hat direction. So we figured out our electric field direction fairly early on, and then we started to think about this dA and all of the different surfaces that our Gaussian surface has. For this case in particular, we chose a box that fits with the symmetry of the electric field here, right? I chose a box that matches the symmetry of the infinitely charged surface in that I wanted to have an A vector and an area vector that points in the z hat direction, and a box is a good choice for that. I also chose a box so that I could make sure that these other edges are going to be 0 when we do the dot product with the electric field. Okay, so we figured that out. We chose our box. We figured out that our edges have 0 flux going through those surfaces. And then we thought about the top and the bottom of those surfaces and what the net flux is going through those surfaces. And because we have this nice symmetry and E does not depend on x and y, we can pop the E out of the integral here, and you're left with just the total integral of the area of our surface that we chose, right? E times A. And we figured out that that's E times L squared here. The bottom has the same exact flux going through the surface because we have a minus z hat area, and then we have electric field going in the minus z hat direction. So we get a similar thing here. So when we calculated our net flux through the whole surface that we chose, through the whole Gaussian surface, we said we did EL squared plus EL squared, 2 EL squared, plus a bunch of zeros, right? That's our net flux through the surface. And then we said, okay, that's fine, but I still have this side of the equation to deal with, and I need to figure out what that Q enclosed is. Well, we know what Q enclosed is based on the geometry and the setup of our system here. So we said that our sigma is going to be, looks like something like dq over dA, and because it's uniform, we can say that the Q enclosed by my surface, sigma is equal to the Q enclosed by my surface divided by L squared, which is the area of that surface there, right? I give you sigma, and we want to figure out what Q enclosed is, so we can rearrange and solve for Q enclosed. Now finally we can put all the pieces together. We can put our net flux together on this side, and we can put our enclosed charge together on this side, put them next to each other, set them equal, solve for E, and then make sure that we put our Z components here at the end. Right? That was the sort of general setup thought process that we took. One thing I want to note is that it's really nice that our surface sort of geometry canceled out. Our ending E field, our final electric field for our infinitely charged surface here, does not depend at all on my Gaussian surface, which that's nice. I didn't want to have an L squared in my final answer because this is sort of an arbitrary box that I chose, and I want to make sure I get some nice electric field that doesn't depend on that arbitrary surface. Okay, so that is the general sort of steps and thought processes that you take to figure out, to use Gauss's law, and to use some symmetry arguments to really simplify this equation. So maybe that's one more thing I can point out here, is that we didn't really have to do this integral, right? We didn't really have to do this integral. We used the power of the symmetry of this setup here in order to simplify the integral into something that is more easily manageable, right? So that's sort of the beauty of Gauss's law, and what you'll get a lot more practice with coming up.